Hello, diamonds in the rough. So let's recap what we have been doing. We tried a gradient descent method with one variable. Right? We had a simple example where we only had one feature and equivalent predicted value, or y you can say, and we try to learn a model from that simple data and try to fit a model. And then once we have like fitted the model, we have found the right weights, we're going to use that right weights to predict the next future example, something like this, right? That we have been doing in this example. As we know, in real world there will be no, like, all the time it will not be only one feature, there will be multiple features like this we have over here, x1 x2. And think like it's a simple example of, like, say, housing price prediction, where you can say there is a one main gate. So this x1 denotes for doors, number of doors in it, and like you can think in that house there are one master bedroom or something like this, and the other house there is two bedrooms, and then third. And this thing you can think of a price, like y values are price. So this type you will have a data. So our goal is to fit a model, right? And the model should used as, like, in future when you have more examples, like if somebody asks you, hey, what will the price for like a house with one main gate and like five rooms or something like this. So with this model you can able to predict that. So that will be our goal. And our goal is not only to like do this problem, but also understand how gradient descent work. We already have learned in the simple example one variable problem, but this time we're gonna do it for two variables. So let's get started. So these are the data as I described you. We can probably plot this data over here on a like a Cartesian plane, and when we plot it, it will look something like this. First example I could write like this. So these x and y, I would say x, this could be your x and z coordinates could act as feature, and the y coordinate could act as the values, like the y values, right? And if I plot it, it will look something like this. It looks two-dimensional, but if think you can imagine it in a 3D coordinate system. And our goal is like how what we generally do is do the best fitting line where our losses are minimum and we could have the best weight which we can use in future. So one initial idea what we had was to draw a line over here, right? And when we draw that line, our goal is to like fit this line. But in this example we cannot fit this line. Like you can see, these two are like little bit separated, so this is not a good idea. And the equation for this line was like some value of mx, like basically the slope and the x variable, right? Simple equation for this line is basically mx, like m will be the slope and x is the like the whatever the input you can pass. So the equation for this line is mx. It doesn't make a lot of sense, it will not fit. So we probably need a better equation of a line, and that equation of line consists of two variables. Two variables, what I mean is like one which will tell you like what will be my slope, and the other, like this basically tells you is what is the angle, the slope of this line, and we have to make sure that slope fits over here. The other part basically tells you the what are the y-intercept values, like on what y point these values will be. So now we have two things to tune over here just to fit these data points. One is to find the right angle, the right slope, right, which fits the data. Another is the intercept value. So this straight line equation requires two variables to fit this data, right? And our goal will be create again the loss function. So loss function is basically like how we can find this best theta is like we need some kind of parameter to tell it that if I'm moving in right direction or not. So we need some kind of function which tells me like if I am in the right place or not. Should I increase this number or something? We need some kind of function. And that function we could make it through the loss function. So let's see. So first of all, we need to understand the predict function, how prediction will be done. Let's say we have random theta, which is not learned. We'll get that theta values. So two theta values because this straight line equation took us two. And those x values over here you can pass on. And if you see, if we have two features, we take individual features, multiply with individual theta and sum them, whatever the result comes, that is the prediction. That we have done in the previous example as well, like with the one variable problem. Same way when we have the prediction function, say from this prediction function we probably can create a loss function, and that loss function formula is basically get the prediction minus the predictor, the actual value, subtract it, whatever the difference is, you square it just to remove the negative sign. And once you have that squared, you can simplify it a bit like this, and you can see in the simplified version we have this x1 x theta values, right? So basically I broke down this predict function, and everything is now in terms of theta 1 and theta 2, and our goal is to find this best theta, right? and what this loss function represent, if we have to visualize this loss function is in input of two main thing is theta 1 and theta 2. So how can I plot this loss function, how can I visualize this loss function? Is basically I'll randomly put theta 1 as 0 0, and then change theta 1 or something like 0 1 1 0, and lot of combination of values I'll put in, and I'll stack the outputs, right? Once I had that kind of table like this, a stacked output, I could probably plot that whole all the data points which we have collected, and I think that will look something like this. So if you look, this is a three-dimensional because we have three variables to cover, so it will probably be a three-dimensional graph, and the loss, all the points which we have calculated will probably look something like this. And if you remember in the previous first example where with one variable we only had this curve, right, which was telling you how the loss function will look. It was a 2D curve, but this time it will be 3D. And in the 3D, as we know, these value, this is the x plane, and you can call this as a z plane, and then we have this y values at loss. Basically whatever the theta, let's say my theta values were like 7 7 something like this, so it was over here, so that for the loss was very high. So if you remember our previous uh, loss function, maybe you remember, right? That loss function, there you can input this theta value 7.7 something like this, and you'll get a very big loss value after calculating. So we plot that point over here, and it's just like that. If we plot so many little points, it will look like a curve like this. Now the goal of the loss function is not to tell you like how this curve looks like. Goal is to use this scatter plot, you can say, kind of thing, to determine what are the right theta values are. And that we have learned from the gradient descent formula. Like how I will know, like if you just create if I just find theta like loss for this point, I'll get 390 for this value. So basically it is telling you are at a very wrong place, you need to move somewhere where this loss becomes 0. And how would I know I have to move in this direction or maybe opposite to this direction? That you can learn from by doing the derivative at that loss function with respect to that theta, right? This is called partial derivatives. I am not sure if how much you are aware of it, but it is very simple to the derivatives which we learned. And the only difference is that when you differentiate this partial derivative with respect to whatever the variable you have to just imagine that other variables become constant, right? You don't have to worry. I'll probably explain it, or if you want a separate video on that, or you can watch, there are so many YouTube videos on partial differentiation which you can probably understand. So over here, yeah, so how we can find this theta, how we'll know that in this direction we have to go, we will find the derivative of that theta point, and which we have learned. Take that loss function, find the derivative, like partial derivative with respect to that theta, and you will probably get a positive value because we want to decrease this thing, and this is subtraction over here. So you will probably, when you solve this thing, you will get a positive value which will tell you to subtract this direction. Let's imagine I was in this other side where the theta values were -7 or 7, something like this. And if you find derivative at this point, probably your derivative will be the negative sign, right? Because you can see this is slope, this is like in a decline. So the slope over here like would probably be like a negative number. A negative will become plus. So this -7 we initially had, it will tell you to move. So this way it will basically tell you to move toward this center point. And not only the center point, from this all direction, like whatever the wrong direction you will tell, your derivative will tell you the right direction, and eventually you will come over here in the center, not this edge as well, but the center where is basically it's like cup shaped, right? Where this is a very cup shaped, I don't know if I'm able to do the justice with the graph, but it's mostly cup shaped, and the center is the basically is the lowest point. And the center, if you see, loss will be very zero. At this point will be very high. So we might need to find those theta over here which has the loss as zero, like very near to zero. And that we can probably, so what we'll do, we'll try different theta values and use our gradient descent method. Eventually we'll reach this loss. If you see this loss is 124 something like that, just say it will go on and go, and I think somewhere around 4, like when the theta values are around 4 and 3, these loss becomes 0, something like this. Let's deep dive how this gradient descent work, how we actually decreased our theta values or increased our theta value. So as you know, we had this loss function. I'm telling you how we can find the update our theta. So this is basically telling you to update the theta value. So this is the initial raw random theta you'll take. And just to know how much to subtract or add from it, you'll find a differentiation of this loss function with respect to that theta. What that means is basically theta 1 is the only variable, like x, y, z or something like this. This is the only variable and the rest of them are constant. You can think just like 8, theta 2 is also like some number. And when we do the differentiation of any constant, it becomes 0, 0 or 1, 0 probably. Like differentiation of a constant value, it's 0 only. So this all probably turn into 0. So that will do. I think I have done the record the steps over here. So first of all, I'll input that how the x1, x2 values looks like in loss function, and then we do differentiation for that. And when you continue, we can probably write this loss function summation function, and then the differentiation will be also written. So how this differentiation, you can see when we do the differentiation of this like square function, 2 always comes. So you can see that 2 is over there. And if you noticed, yeah, so you can probably check this out by yourself, use some pen and paper, try to solve this. You will probably see this answer. And we have wrote in a summation form. So when you do that, you will probably find this gradient. We call it gradient over here with respective thetas, like with respect to their partial differentiation. We have got this gradient, and we can use this gradient to accommodate our theta values. And once we do the repetition, we'll probably find some better theta values. So randomly, we can start with 7, 7. Learning rate you already learned. Learning rate helps you to tell you that we only wants to know the direction in which we want to subtract this value. We don't want all the magnitude, because we can jump from the local minima, right? The best theta, because if I have a very big number to subtract, I might jump around the local minima and never reach there. So the best idea is to start with like slow steps, so that I don't jump over that value. So only need direction, like I only need gradient to have the direction in which you want to subtract or do addition, not their like magnitude. So when we start with 7, 1, 7 theta, our losses will be something like this. 54. So the gradient, like this is the sign of the gradient. So a lot of places you will see this triangle as the sign of gradient. So gradient for this loss, right, which for theta 1 and theta 2. So basically this part, if I solve, I'll get 54. This part I'll solve, I'll get 120 when the input was 7. So if you input theta 1 as 7 and theta 2 as 7. So both, if I solve this point and this point, I'll get 54 and 120 when the input was 7, 7. And then that value I can write, I'll have this learning rate and multiply. You can see I'm going in the, like theta got decreased to 6.5, 5.8, something like this. So this will carry on, and with new thetas what I've got, I just loop back again and we'll solve it. You'll see the loss is decreasing, and you can see again with more iteration we are moving in the right direction. At some point at like very close by 4 by 4, we were able to get the right values. And it's not that we have to only try like 7, 7. You can like try with -7 or 7 as well. Any number you can try, and probably will end up at 4, 4. With -7, you can see our derivatives, like the gradients are a negative sign, which is telling, hey, you are in the opposite side of the minimum point. So make sure so this negative will become and tell you, hey, you're on the loss side, you need to add your number up. So this will tell, hey, you need to add more. And as you progress, these values the theta values will change into a positive direction. You can see this is increasing. With few more direction, we'll probably again come back to 4 by 4. So there's not much different with first variable problem which we did previously, and second one is like you have to do this like gradient, like the derivative part with respect to the variable which we are dealing with. So that is the difference from the previous example. The rest it will be same, and this the same thing will work with more feature. Let's say in future you have x1, x2, x3, 4, right? and that time it becomes a multi-dimensional feature, and I cannot probably even plot it on it like three-dimensional space, and to divide to have this model fitting on, right, just like we had this model fitting thing on those points. Now we probably required not just a single line, a plane. Plane, if you remember, plane has three variables like x, y, z or something. A plane would fit on those data points because it will be multi-dimensional. Maybe a circle will fit or something like this. So there will be more variables in your model. So these prediction values will have more x values like x0, x1, x2, x3 or something like this. And you don't have to do much, just like this increase the number of features like this, and probably that will increase your theta values, and this method will work over there as well, and you will find derivative with respect to each other, theta 1, theta 2, theta 4, and same will be, and you will get gradient for that. Use that gradient to update the theta values, and it will be same. So I hope you understood this part and how we can roll and find our various theta number of thetas, weights, right? And once we have found the weights, we can use our desired weight which we have found, like fine tuned you can say, and we can see an example where like x1 is one, like a house with one big gate and 4 rooms. So what will the price for that? We can probably use our prediction function, the theta, which we have done so much hard work to find that. We'll use our theta, the best one which we found, and the input, the new input, and probably solve this, basically multiplication and addition over here. And when we do multiply, it looks something like this, and we'll have this value. I think it becomes 16 plus 4, it becomes 20. So the prediction for this example will be 40, and as you can see, it looks quite right to me. And so this way we'll probably understand how this works. So I think that was for today's video. Do let me if you have any doubts or something like this, or if I not done justice to any of the part, I will probably help you in the comment section, or maybe we can make a future video on it. And do let me know if you need something on the partial differentiation side. It's pretty easier. You can do, and anything, one thing you can do whenever you stuck or something, just take this screenshot and probably can ask ChatGPT something. It will probably help you to explain that. So I hope you have understood this, and I'm pretty excited for the next part, because now I would say we are quite done with regression, and we're moving toward classification, and we'll see how things change over there. Like does the loss function stays the same? What is the method over there? Simply like this, we'll probably start with a simple example with little features and little values where the calculations are easier and easy to understand, and we'll see what are the differences we learn over there. So I'm pretty excited for that. I hope you have subscribed, have notification on, so that when that part comes, you are there. So see you.